Lawrence Livermore National Laboratory, where we are right now, recently declassified over 100 film recordings of the above-ground nuclear tests that the U.S. conducted between 1945 and 1962. These films are free and available to the public on a playlist on our YouTube channel, and as you guys have been watching them, you've been asking some interesting questions regarding some of the things that are happening in these films. Lawrence Livermore nuclear physicist Greg Spriggs is here to help me answer some of those questions today. We're going to use this laptop here to take a look at some of our test films.
Fantastic.
We stopped above-ground nuclear testing in 1962, and we stopped underground nuclear testing in 1992. So aside from being an interesting relic of our nuclear past, what do these test films help us do?
The data that was obtained from these detonations is used today to help validate our computer codes. Since we stopped testing nuclear weapons, and as a result, we also stopped designing nuclear weapons. So now we do everything with big computer codes and simulations. But the code is a computer code, and it may give you a bogus answer, and you need to validate that against some real data. And this benchmark data that we obtain from the films is basically what we're normalizing our computer codes to. So these are very, very important films.
What new things can we see now that the films are on a computer that we maybe couldn't see when they were in physical form?
The way they read the films back in the 1950s, they used a device called a codograph, which was basically just an image enlarger. And it involved humans putting this film into this codograph, measuring, moving things around, and then trying to read it by eye. What we're doing now with the computer, though, is we're able to read the optical density on the film and get a much more accurate measure of the shock wave as a function of time. And so the uncertainty of the yield determinations has dropped from about plus or minus 10% down to about plus or minus 1%.
Sure, not as much human error.
Instead of taking weeks to measure one particular film, it now takes us just a matter of minutes to do it.
Yeah.
So we're able to analyze more films than what was done back in the 1950s, and we end up with much more accurate data and a more complete record of what the data is on that film. So this is what the value of these films are now. There are things that we're doing that they didn't even think of doing back in the 50s or didn't have the technology to do.
So we've got more data, more accurate data, new techniques, and we're using all of that to plug into the computer codes that we use now to simulate nuclear detonation.
That's correct.
From beginning to end, can you sort of walk us through the big basics of what's happening in each of these detonations?
When a nuclear detonation goes off, you end up fissioning uranium or plutonium, some sort of nuclear fuel, and it produces this huge amount of energy in a very small volume. There are 4 effects caused from a nuclear detonation, 4 major effects. The first one is prompt radiation that's being emitted by the fission process. So you get prompt gammas and prompt neutrons and neutrinos and so forth. The next effect that we see is the thermal output. When the detonation occurs, about 86% of the energy that's released from the detonation goes into heating up the air, so the air becomes very hot. The third effect is the shock wave, this high temperature plasma that's formed in this primary or in the weapon itself starts to push on the surrounding air, and it creates a shock wave. And that shock wave is moving very, very fast. It's moving about Mach 100, and as a result, it's very, very hot. So as the shock wave expands, it starts to cool. And in this film here, as you watch it go out, you see it's bright initially, but that's because the shock wave is very, very hot, putting out lots of visible light.
Right.
And the next frame, the intensity comes down a little bit, and the reason it comes down is because the shock wave is considerably cooler, but it's still hot enough that it's opaque to the hot gases on the inside. So we have this very hot ball of gases, but you can't see it. All you're really looking at is the surface temperature of the shock wave. When the shock wave finally drops down below the Draper temperature of 525 degrees, it disappears off the film, and it's completely transparent to light, and so as you continue out a couple more frames, the light intensity comes back up again. And that's because the hot gases are now able to shine through.
I see. So it's almost like the shock wave is like the shell covering up the hot gases on the inside, and once that disappears as it cools off, then you've got the hot gas on the inside.
Exactly. So there are 2 distinct pulses associated with a nuclear detonation. You don't see that with a conventional weapon. The reason is that the gases inside a conventional weapon don't get nearly as hot as they do on a nuclear detonation.
I see.
So this particular shot was out in the Pacific. It was a tower shot. They put these on towers on this particular island out here, and I believe this was Inuitak. The moisture out in the Pacific was always on the order of almost 80 to 90%. Most of the time it was close to 100%. So you get this Wilson cloud effect, which obscures the fireball. When we do airdrops, we don't have a Wilson cloud. Usually the airdrop is up high enough. In the Pacific, whether you did it up high enough that you didn't have that much moisture, or at the Nevada test site where the normal surface humidity was very, very low. So you don't see this Wilson cloud on most of the airdrops. So this is the Wilson cloud. As you go out a little bit further, the prompt radiation dies down, the Wilson cloud disappears, and you can now start to see what's on the inside of that Wilson cloud. You see the bomb debris. The early cloud is actually starting to form at the very top up there.
Okay.
In this particular case, it brought coral into the fireball, and that coral got very hot and sort of got scorched, and so you're looking at the bomb debris, the smoke, and burnt coral that got sucked up into the fireball.
And so this was, as you said, a tower shot?
This was a tower shot.
Okay, and then are there just only two kinds, tower shot and one that's dropped?
They did several different kind of shots out in the Pacific. One of them was called a barge shot. These were the very high yield ones. They didn't want to drop them out of a plane, so they put them on a barge, and they would float the barge out into the deep water region around the Pacific. And then they did another series of shots where airdrops out in the Pacific. Most of these were done during Operation Dominic in 1962, and those really show the double pulse that I was trying to explain earlier. At the Nevada test site, they added one more category. They had these helium balloons. They would put the bomb into the gondola underneath the balloon, and they would tether the balloon onto the surface. And they did about 40 different balloon shots, and they stopped doing it. The top part of the fireball was distorted because of the helium balloon. And then they had these lines, these tether lines, and you would see these spikes coming off of the bottom of the fireball, which was the cables that were actually vaporizing during the detonation itself.
Oh, because that's one of the questions that we often get on some of these. I think I've got one of these. Some people call them like the protrusions or the legs that come off the fireball here. This is a function of how they were carried to their detonation site.
Right. All right, so that was a tower shot. So if you go a little bit further, and you can see those spikes again, but you'll also see the towers vaporizing right below it. And these towers, it was basically just a big elevator shaft. And again, they had cables that would tether this tower to keep it upright. And you could see the cables were starting to vaporize in addition to just the tower itself underneath there.
These protrusions, which are its tethers and the tower, are lighting up faster than the sphere of the explosion. Why is that? The
shock wave is very, very hot. It could be on the order of 500,000 degrees. When it's very, very hot, it puts out X-rays, and the X-rays go through the atmosphere and they interact with the cable and the tower. So out in the air, you don't see the interaction of the X-rays with the air, but with the cable, since it's a much higher density, the X-rays interact with it and cause it to vaporize, and that's why you can actually see the cables. So really on the outside of this fireball, or a bunch of X-rays that are being emitted by that shockwave surface because it's so hot. It's just on the cables you can see it, and in the tower you can see it.
Right, so if anything else solid were around this, we would be able to see that due to the X-rays?
Due to the X-rays being emitted by the surface.
Well, let's talk about this one because it's a great example of another frequently asked question, which is the streaks in the air behind some of these clouds. Can you tell me what those were used for?
As the shock wave moves out further and further, it gets cooler and cooler. And when it finally reaches 525 degrees centigrade, the vapor temperature, it no longer emits visible light. And so the film, which is only sensitive to visible light, it looks as if the shock wave disappears off of the film.
I see.
So they came up with this trick. They said, hey, when the shock wave finally disappears, what we can do is we can put out these smoke trails. And we have at the shockwave front this very high density air region, and then on the outside of the shockwave we have ambient air. And we can use the optical illusion effect to illuminate where the shockwave front is. And it's the same effect. You've gone from a low density air above the straw to a higher density region, which is the water, and it looks like the straw is broken.
Right, so the straw comes in here, and then once it hits the water, it looks like it goes down here.
So what happens is the shockwave, as it moved away from the detonation point, there was this optical illusion with these smoke trails, and it formed these little hooks in these contrails, but it actually didn't interact with the contrails. It was just a little hook that was caused from an optical illusion from that effect there.
Oh, wow.
So about 5 seconds before every detonation, they would show up these rocket trails, and these trails usually were about halfway between the camera and the detonation point. In this particular case, there's another set of cameras on the other side which actually show the hooks as the shockwave moves out.
Wow.
So they could follow the shockwave out further, and that would help them understand shockwave physics. For these nuclear detonations, they wanted to capture a larger portion of the light output as a function of
So you've
time.
got something that's hugely bright.
Very, very bright. So they used a film called microfile, which had silver halide crystals in it that were actually on the order of about a micron. Very fine-grained film.
Yeah.
You could actually blow that film up with an image enlarger maybe 100 times, 200 times, and still not see the grain.
Wow.
These particular films, the ones that were done on the microfile film, the speed on it was 0.1. As opposed to normal range film of 200 to 2000. So it was very, very hard to expose unless you had a nuclear detonation.
Of course.
And the nuclear detonation was bright enough that it would actually activate the film even during the high-speed photography of it. So they're very, very bright. When a nuclear detonation occurs, the light output from a nuclear detonation changes by about 12 orders of magnitude. The best film that Kodak made, which was the microfile film, only captures about 4 orders of magnitude of that variation. And so that's what you're seeing on this film is 4 orders of magnitude of light variation. And it was done very, very early in the morning, so there was no backlight to mess up the photography. And unfortunately, if they didn't time it just perfectly, it stayed dark a little bit too long. And so this particular film, it kind of disappeared off the film because it stopped glowing.
Since we're talking about the film, we've got these numbers down at the bottom of most of these test films. What are these keeping track of?
When we render the film, this particular scanner that we're using is a true frame-by-frame counter. It captures each individual frame, and we like to keep track of that so that when we measure the data, we have an absolute reference number here. So that we just simply put the frame number down at the bottom.
I see.
It doesn't refer to time or anything. It's just a frame counter.
I see. Are they recording the explosion in real time? Are these slowed down at all?
The shock wave is moving at Mach 100. It's moving very, very fast. So the only way you can slow that down and capture it, you have to use a high-speed camera. Most cameras, the standard Hollywood camera, runs at 24 frames a second. When they're trying to capture the shock wave as a function of time, they wanted to run it at 2,400 frames a second, about a factor of 100. That was fast enough that they could capture this, and then when you play it back at normal speed on a video, it plays back at 30 frames a second. It looks like it's running in slow motion. So they had about 10 of those kind of cameras that were capturing the early cloud, and then they had another series of cameras that were used to capture the late cloud. Well, the late cloud, it takes about 7 or 8 minutes for the cloud to reach the top. And so they adjusted the speed on those cameras to 1 frame per second.
Whoa.
So that was moving much, much faster. So it was a time lapse.
Interesting. So this is so we can get as much scientific data from them as possible.
Exactly.
The last commonly asked question that we get on a lot of these films is what happened to those places after the tests were conducted, and if we were to go to them now, would we be able to tell? Are there any lasting impacts from the tests that were done there?
At the Nevada test site, after the atmospheric testing was done, they went underground and they started making what were called subsidence craters. So you would detonate this several thousand feet underground, and it would vaporize a certain amount of soil underneath, which would then cause a cavity to form, and then the weight of the soil above would basically collapse into this cavity, and it would cause a crater on the surface. Those are called subsidence craters. We did about 800 of those underground tests, and we did 200 atmospheric shots. So if you went out to the Nevada test site, you might be able to find maybe a half a dozen different areas where they had the original fallout plume where it went to the ground. They usually have it fenced off, so you can't get into it. They monitor this constantly. They have remote solar-powered monitors out there so that nobody happens to wander into it, and they can monitor it. They do a lot of cleanup out there also. So if they had one site they wanted to clean up, they would basically go in there and scrape off the top 4 or 5 inches of soil and put it in barrels and bury it.
Wow.
So the site out there is basically pretty clean. So yeah, there's not very much out there anymore. It's just they maintain it because it is a radiation area. In the Pacific, they did a lot of shots at the Bikini Atoll and Inuitak, and those areas are closed off to the public. They actually went out and did scrape off some of the coral sand that was on the surface that was contaminated and replaced it with fresh sand. But when you go out into the lagoon itself, there was no way to practically clean up all of that radioactive material that's underneath the water. So it's basically closed off to the public, so you really can't go out and see that.
We use these test films to help validate our nuclear models that we use on our supercomputers. But why would you say is that important, Greg? Why are we doing that?
We use the atmospheric test data and some of the underground test data to basically validate our computer code so that we can continue to monitor the nuclear stockpile for the United States and certify that indeed if we ever have to use it, that it would work the way it was intended to work.
Okay, well, I think that answers all of the frequently asked questions, Greg. Thanks for stopping by and talking to me about it.
You're welcome.
Really appreciate it.
Thank you for having me.
We learned a lot today, not only about our country's nuclear testing past, but also what we're still learning from these films decades later. It's all part of this lab's responsibilities around something called stockpile stewardship. And we have a video coming out soon on what exactly that means. So subscribe to this channel and stay tuned. This is something that's important to learn about and understand today, so leave your questions about it down in the comments below. Thanks for watching, and we'll see you next time.